Hello everybody, and welcome back to another CIV 398 assignment guide. So in this guide, we're going to be covering question 2 of assignment 3, and this is when stuff starts to get new. As we saw in question 1, it was more or less a review of assignment 2, it was just straight up linear algebra. But now we're getting into the fun stuff, which is the straight up continuum mechanics. So I really like this, and I hope you guys will too, because now we're going to take everything that we learned in linear algebra, which was just, honestly, let's be honest, it was just a bunch of numbers. But now we're going to give it some actual physical meaning, and we can actually start to visualize what do these numbers represent. And the first step will be right here in question number 2. So question number 2 says, determine the limits alpha for the following position and displacement functions to be physically possible. So the key here is that we want to figure out alpha, and if we look at these equations, each one of them has alpha somewhere. And we got to determine alpha to make sure that these are physically possible. So we're going to have to talk about, okay, what makes what makes a set of position functions or displacement functions physically possible? Now, the key here, I just want to say straight off the bat, I want you guys to realize that if we look at A and B, all those functions are in terms of x1, x2, and x3. So these are called position functions. If they're in terms of small x1, small x2, small x3, they're position functions. Now, if we look at part C, instead of x, we have a u. And this is called a displacement function. And as you guys saw from the quiz video, I hope you guys know what the difference between small x is as well as u. But for this assignment, make sure that we know the difference because we're going to have to do a little bit of tweaking when we start calculating alpha. So the goal of this question is very simple. We have to determine if these are physically possible. We have to determine alpha to make sure that the deformation is physically possible. So we have to ask ourselves, well, how do we know if deformation is physically possible? Well, we look at the determinant of the deformation gradient. And wow, that's a mouthful to say. So the deformation gradient we call f. And right now, you guys may not know what f is, but don't worry, we're going to talk about it. Just know that f is going to be a second order tensor or a 3x3 matrix. So we know how to find the determinant of a 3x3 matrix. And the following is true. If that determinant of f, which again is going to be a 3x3 matrix, is greater than 0, this means that our deformation is physically possible. And on the other hand, if the determinant of f is less than or equal to 0, this means that the deformation is physically impossible. So you guys know how to find determinants of f. It's just a 3x3 matrix. You guys know that since some of the components are going to be alpha, we're basically going to have an equation as a function of alpha, and it has to be greater than 0. So on paper, this sounds really easy. We have one equation with one unknown, alpha, and we have to determine the limits of alpha for this deformation to actually be possible. But let's take a step back and say, okay, Clayton, you said the determinant has to be greater than 0 for this deformation to be physically possible. And well, I'm not going to take your word for it. So what exactly does this mean? The determinant is greater or equal to 0. So let's say that the determinant of f is equal to something called j, and even though it's a bit more complex than just this, it's basically the ratio of the volume after deformation compared to the volume before deformation. So that V there would be the volume after deformation, and V naught would be our original volume. So if we look at this and say, okay, well, if the J here, which is our determinant of F, is less than or equal to 0, which means something is physically impossible, that means that the volume after deformation is negative. And that makes sense because how can a volume become negative after we deform it? I don't push, let's say, a brick and the brick just disappears. that would actually result in a lot of questions that I don't know the answer to. But this is why we say that it's physically impossible if the determinant of f is less than or equal to 0, because what this indicates is that our volume after deformation is either negative or 0, which of course you guys can imagine makes no sense at all. So now we got to figure out, okay, well, this question is just as simple as finding the determinant of f. But what is f? And now this is where I'm going to scare you guys, and I really don't want to scare you guys. F is equal to the partial derivative of x1 with respect to big X1, big X2, big X3, and then the partial derivative of x2 with respect to big X, and the partial derivatives of x3 with respect to big X. And I know you guys are looking at this and saying, shit, this class is not going to be fun. But don't worry, even though it looks like garbage, it's actually really easy. So the first thing that we have to understand is that f right here is going to be a second order tensor. Well, what does that mean? It's going to be a 3x3 matrix. And you guys are thinking, well, if all the partial derivatives weren't in there and I just have f in terms of numbers, and it's just a 3 by 3 matrix, well, then it's easy. Because for a 3 by 3 matrix, I can easily find the determinant. And if I find the determinant and it's going to be in terms of alpha, well, I have my one equation, one unknown. I can easily solve for that alpha. So the question becomes, okay, well, how do I find those components? What is partial x1 with respect to big x1, stuff like that? So what I'm doing is I'm just going to show you guys a little sample calculation. So I just pulled these numbers out of my ass. They're not actually in your assignment. These are just random numbers to show you guys. So let's say that I have small x1 as 3 big x1 plus big x1 squared plus 4 big x2 and 4 big x3. And let's say I wanted the partial derivative of x1 with respect to big x1. So you notice how I highlighted big x1 in red. Well, what I do is I look at my equation and I'm only interested in all the terms that have x1. Because if I look at, let's say, 4x2, well, I can see that the partial derivative of that is just going to be equal to 0. So all I'm doing in this equation, if I'm looking at it with respect to big x1, well, I'm going to highlight all the terms that are big x1, and I'm just going to differentiate them. So 3x1, the derivative of 3x1, well, that's just going to be 3. The derivative of x1 squared, well, that's going to be 2x1. So in the end here, I have 3 plus 2x1, and then the other two terms, since they're not in terms of x1, they're x2 and x3, I just go plus 0 plus 0. So the partial derivative of small x1 with respect to big x1 is just going to be 3 plus 2x1. Now I can carry this on and say, okay, well, now I found the partial derivative with respect to big x1. I can find the partial derivative with respect to big x2. So notice how I have big x2 highlighted, and I go into my equation and say, okay, where are my terms with big x2? And I say, oh, there they are. I have a 4 big x2. So if I take the derivative of 4x2, I just get 4. So if I look at the equation, it's basically 0 plus 0 plus 4 plus 0. So in this case, partial x1 with respect to big x2 is just going to be 4. And I can repeat the process for x3. So if I look at my equation, there's only one term with big x3, which is 4x3. I take the derivative of that, I get 4, so my value is just going to be 4. So as we can see, even though it looks like absolute garbage, it's very easy to figure out. And if I were to look at the first row at my deformation gradient f, it would be 3 plus 2x1, 4, and 4. So then I can repeat this for x2 and x3, and I'll have my deformation gradient f very simply. It's not too bad at all. Now, remember that part A and B were position functions. They were x1 and x2. So with that, I can say, okay, I got x1, x2, and x3. I can find f, and then all I have to do is take the determinant of f and make sure it's greater than 0 to find alpha. But if I remember part B, I wasn't given x. I was given u, which is a displacement function. So what happens if I'm given a displacement function u rather than the position function f, or position function x? Because remember, in order to calculate f, the deformation gradient, we need x1, x2, and x3, not u1, u2, and u3. But as you guys may have guessed, there actually is a very nice relationship between our deformation gradient and something called the displacement gradient. So if I were to do the same process as before when finding the deformation gradient, where I just take the partial derivatives of all the x's, well, I can do the same thing with all the partial derivatives of the u's. And this is called the displacement gradient, which is symbolized as nabla u, which is that upside down triangle times u. And there's a relationship between the two. And what I'll find out is that f, my deformation gradient, is equal to the identity matrix I plus the displacement gradient nabla u. So if I expand this out, I say, okay, well, then f is going to be equal to the identity matrix, which is just the diagonal components 1, 1, 1, and the rest is 0, plus our displacement gradient nabla u. And if I look at the equation for nabla u, I can see that this is actually just going to be the same as the deformation gradient, except I'm just taking all of those x's and I'm replacing them with u's. So just a quick recap, we have our I, which is the identity matrix, and then we have our displacement gradient, which is nabla u. And again, nabla u is the same process as before, but instead of taking all the partial derivatives of x1, x2, and x3, I'm taking the partial derivatives of u1, u2, and u3. And if I wanted to, I can expand it out. And as you guys will see, I can easily get f if I know both the I, which of course you guys know I, as well as nabla u. And again, once I know f, I can take the determinant of f, make sure that it's greater or equal to zero. Sorry, not equal to. It has to be greater than 0, and then I can solve for alpha. So this concludes question number 2. I hope it helped. I know it's a little bit scary looking at the deformation and displacement gradients at the first time. They can be a bit overwhelming at first, but hopefully I showed you guys that solving them is pretty simple once you guys know how to do it. So thank you guys so much for listening. I will see you guys in question number 3.